Hi everyone, welcome to this episode of Keipert Labs. In today's video we're going to be talking about substitution reactions. So we're going to start by understanding what we mean by a substitution reaction. We're then going to go step by step through the mechanism of a substitution reaction, what happens and what are the steps involved. We're going to look at a concept called polysubstitution, and then we're going to look at the reaction conditions involved in a substitution reaction. So firstly, what do we mean by a substitution reaction? Well, the name itself is fairly self-explanatory, that we are substituting a hydrogen atom in an alkane with a halogen atom, like chlorine or bromine. So we are swapping the atoms around. We are including it into the structure. So for example, if we go from methane, the hydrogen labelled in blue has swapped for the chlorine atom labelled in red to make our new product. So how does it actually happen? Well, let's break it down step by step. Okay, so if we've got here, I've done a little bit of color coding to try and help us visualize how this works. So we've got methane on the left, and we've got a molecule of chlorine gas on the right. So firstly, this reaction involves UV light. And what the UV light does is that it breaks the covalent bonds here and here, just like this. What that does, once those bonds have been broken, is that we have what we call radicals that have formed that contain these unpaired electrons. That's what these dots represent. So it's basically like we've undone the process of forming the covalent bond by overlapping the electrons. We've reversed that process. Each of the atoms that was connected previously now has one unpaired electron sitting on itself. But of course, that's a very unstable situation to be in. And so then what happens is that naturally through the movement of these particles that these radicals swap places. And what can happen then is that we get new connections that get made, new covalent bonds that form as these unstable reactive radicals kind of bump into each other. And so we've got these new covalent bonds. In the end, we've now substituted a red chlorine for the blue hydrogen that they've swapped places. And in doing so, we formed what we call the hydrogen halide. That is, in this case, HCl, or if this were bromine, it would be HBr. Okay, so this forms as a gas, that if that gas dissolves in water, it forms an acid, hydrochloric acid or hydrobromic acid. Okay, that's one way that we can confirm that this reaction has taken place. So we've swapped a hydrogen for a halogen, and by doing these various kind of stages. But imagine for a moment that we had just, we got the mixture just right. We're saying, all right, well, what's to say that the reaction stops? Because this molecule's still in there, it's still got hydrogens that could be substituted. So we could have substituted one, and then a second one, and then a third one, and then eventually a fourth one, that we end up with what we call polysubstituted alkanes, or a mixture of these different compounds that these products that have varying numbers of these halogen atoms substituted in. Now, depending on exactly how much we combine, this may or may not be very likely. But if we have an excess of the halogen, then what we can end up with is we can get all of the molecules have gone all the way to completion over time. And we end up with this tetrachloromethane compound that we see here. Now, the reason we end up with a mixture of products in most situations is that if imagine for a moment you've got a mixture that's got 1,000 methane molecules in it to start with. Okay, well then one of them reacts and forms this chloromethane. Now it's true that this chloromethane can go on and react further, but there's 999 other methane molecules that are more likely to be bumped into first. And so therefore we tend to get more of the mono-substituted product, this one, than we do of any of the others, because the chances of those specific molecules interacting and reacting with the radicals that form is lower and lower as time goes on. Only once they've formed chloromethane, and then it's all forming dimethylchloromethane and so on from there, that you get more and more of these substituted products that form, and it requires a significant excess to get the chances of these molecules bumping into each other to be high enough for this to be seen. Now, yes, we do form this mixture. The mixture happens quite commonly with these sorts of reactions, but these products have different physical properties. And so we can actually separate them from each other using processes like fractional distillation. if we need to confirm, okay, well, we can end up with a pure, say, chloromethane. Like here, if we want to separate this from anything else, there are ways that we can do that. Okay, now how do these reactions happen? What do we need to do in order to make sure that this happens? Because there's certain kind of boxes that we have to tick. The first one, as I mentioned in the mechanisms kind of stages, is that we need UV light, or high energy specifically, but UV light is the most common. Because we're trying to break stable covalent bonds between the carbon and the hydrogen, the carbon and the chlorine, and the chlorines from each other. I realised that typo there. Okay, and so high energy is needed to make that happen. Now, yes, we could have high energy in the form of heating, but heating and hydrocarbons tends to be a bit of an interesting combination. Okay, you're more likely to get it to combust rather than to get it to undergo this kind of reaction. We call this sort of reaction a photochemical reaction, where the light is necessary or is involved in making this change happen in a way that doesn't cause combustion. Okay, so UV light is necessary. If you do it in the absence of UV light, it doesn't happen. And likewise, the reaction is quite slow at room temperature. So even with the UV light, that this reaction is not very rapid. Maybe 5 or 10 minutes for a small sample that has sufficient excess. But for larger samples, we might be talking a much longer time scale. Okay, and it only occurs when we are reacting with chlorine and bromine, because fluorine is too reactive, whereas iodine is too unreactive under normal lab conditions. So that we're only talking about chlorine and bromine being able to be added in this situation. So we've looked at what is a substitution reaction, where we're swapping a hydrogen atom for a halogen in a hydrocarbon molecule. We looked at the step-by-step mechanism involved in actually kind of forming these compounds. We looked at the idea that if we keep going, we can actually end up with more halogen atoms substituted, but it becomes less and less likely, and also seeing the reaction conditions that we need to get the substitution going. Thanks very much for watching. Don't forget to hit like and subscribe. Bye for now.